Hey team, it's Mr. Lackey. You're watching this video because you missed live class this week with either me or Mr. Holderman. Remember, if you want to avoid watching these recaps, you should just come to live class. Okay, today it's going to be pretty short. There's just a couple little highlights that I wanted to add on to the notes that we did earlier this week. And then at the end of this video, I'm going to give you a couple of links for some review questions about ionic and covalent bonding that we did together during live class. So let's go ahead and jump right into some covalent bonding. So what we're going to look at here is last week when we did ionic bonding, we compared how the electrons move between two atoms. So let's just go ahead and let me move some things around on my screen here. Okay, let's start with two examples that we're going to see. So remember, of course, when we talk about covalent bonds, we're always having non-metals. So I'm going to just start with two standard non-metals. So let's say I take carbon and I take hydrogen, okay? I know those are both nonmetals. Carbon's from the right side of the periodic table. Hydrogen's the one exception of nonmetals found on the left side of the table. Using those same skills from last week, if I look up where that's from, carbon is from 4A, which means it's going to have 4 valence electrons. This is one of those skills that now something from last semester is important again. So when I draw the 4 valence electrons, remember I space them out. I don't put any of them together until each side has one. So I'm going to say 1, 2, 3, 4 valence electrons, one on each of the 4 sides here. Hydrogen is from 1A, so it only has 1 valence electron. Now, last week we did this thing where we drew these electrons being shared, like hydrogen was often giving away an electron. In this case, we are actually going to see something different happening. So when I have two nonmetals, instead of an electron being given away, we're going to talk about how electrons are going to be shared. So the shared electrons are usually electrons that are hanging out by themselves. So for example, all of the electrons that I can see here are candidates for sharing. Let me give you a different example. If I were to look at something like oxygen, so remember oxygen has 1, 2, 3, 4, 5, 6. Only the electrons that are by themselves are good candidates for sharing. The ones that are kind of paired up already, they're not going to be ones that the atom is likely to share. Okay, so going back to our examples over here of carbon and hydrogen, that means we could share a pair. So I'm going to go ahead and show you a pair that could be shared. Okay. So these two electrons might be shared between the carbon and the hydrogen, and that's going to create a single covalent bond. So remember, covalent bonding is when atoms share electrons. What has happened here is now both atoms get to act like they have those electrons. So for example, hydrogen's happy because it filled up its shell to 2, because remember, hydrogen only is in that first row of the periodic table. We would say that carbon is not yet happy though, because if I count up its electrons, I got 1, 2, 3, 4, 5. What we can see here is that similar to last week, we should remember that in the world, carbon atoms don't appear by themselves, and neither do hydrogen atoms. If there's one hydrogen atom around, there's probably a bunch of hydrogen atoms. So if I were trying to make a prediction of what could happen, if there's other hydrogen atoms around, carbon has the opportunity to make all kinds of bonds. So carbon can actually pair up with 4 different hydrogen atoms at the same time. Notice each hydrogen is happy because each hydrogen has 2. 1, 2, 1, 2, 1, 2, 1, 2. And then if I count up the ones around carbon, it ends up at 8. 1, 2, 3, 4, 5, 6, 7, 8. So everybody's happy here. This would be our CH4 would be our formula. We'd call that carbon tetrahydride if we go back to our naming from earlier this week. I'm going to give you guys another more simple example. So let's go ahead and take a look at something like, say, fluorine and chlorine. Both of these are from 7A on the periodic table. So if I'm going to go ahead and start numbering these, I have something like 1, 2, 3, 4, 5. I'm going to skip this one for a second. 6, 7. I drew it that way because I know how the bond is going to work out. Chlorine is going to have the same number of dots. So I'm going to have 1, 2, 3, 4, 5, 6, 7. Okay. So basically, these two, they're both from 7A. They both have 7 valence electrons. They really just need one more electron to make them happy. So if they can't pair up with something, say, like a hydrogen, if these two atoms appear next to each other in nature, what they can do is they can just do a little bit of sharing. If they share these two electrons, now chlorine's happy and fluorine's happy. If I count these electrons towards both atoms, they're both at 8 and they're both happy. So that's why the sharing works out best for them. Again, we call this a single covalent bond. Anytime two electrons are being shared, that's one covalent bond. Notice actually, because of the way that we wrote this, really anything from 7a is just looking to make one covalent bond. And what will happen often is instead of a fluorine, like we just drew up there, encountering a chlorine, because atoms don't tend to appear by themselves, they tend to appear in packs. So wherever there's one fluorine atom, there's probably a ton of fluorine atoms around, which means very, very often, fluorine will actually pair up with a second fluorine atom. So a lot of those things from 7a, many of them are what we call diatomic molecules. So you guys learned that prefix in this unit, di meaning two, atom meaning atom, and molecules meaning bigger than an atom. So diatomic molecules are things like fluorine. That's because fluorine tends to appear in nature in pairs. So does iodine and chlorine and bromine. And in fact, hydrogen also tends to appear in nature in pairs because it can share just that one with another hydrogen to make itself happy. You don't have to memorize these, but I just want you to have heard that word before, diatomic molecules. They tend to appear in pairs in nature. All right, I wanted to show you guys one other thing here, just because it's an idea that was glossed over in the notes. So let's do one more example. So let's say I take something like sulfur, which is from 6a. So I got 1, 2, 3, 4, 5, 6. And then I'm going to take something like, let's go with oxygen. 1, 2, 3, 4. I'm going to skip over here, 5, 6. All right, so they're both from 6a or 16. They've both got 6 valence electrons. What you might notice here is we've got an opportunity to do more sharing. So for example, I can do, these two can share, right? So now each of them gets up to 7. 1, 2, 3, 4, 5, 6, 7. Same count is going to apply on the bottom, right? They both just need one more. Well, look, they've got another candidate. This little lone electron is another candidate for sharing. So now what they're going to do is they're going to share twice. So they can share these two as well as these two. So overall, these two atoms are sharing 4 electrons. This is actually what we call a double bond. So we call this a double bond because the two atoms are sharing more than 2 electrons, right? If they just share 2 atoms sharing 2 total electrons, that's a single bond. This is also a single bond. This, however, is what we call a double bond. All right, over here then, just for comparison's sake, notice that this, we would actually call this, we would not call this a quadruple bond. We would call this 4 single bonds, right? Because this carbon has a single bond with this hydrogen. It has a separate single bond with this hydrogen. It has a separate single bond over here, and it has a separate single bond over here, right? So there's a whole lot going on in terms of trying to figure out the difference between single bonds and double bonds. Let me do one last example to kind of help clarify what we're talking about here. So sometimes covalent compounds are even bigger than 2 elements. So let's say I had something like, let's say I've got carbon, 1, 2, 3, 4. Maybe I've also got some oxygen, 1, 2, 3, 4, 5, 6. It's from 6. And then let's go ahead and throw a couple hydrogens in the mix. Okay. Carbon, again, remember, it's really versatile. It can bond with a lot of things because, look, it's got 4 candidates, 1, 2, 3, 4, to make covalent bonds. Hydrogen can't make more than 1 covalent bond. Oxygen can only make 2 covalent bonds, right? So if I were to go ahead and say, okay, well, I can make this oxygen happy with just the carbon, right? If I take a look here, I can count up and say, well, I've got my oxygen happy 1, 2, 3, 4, 5, 6, 7, 8. And now I've also got some more opportunities for bonding over here on the left side. I can go ahead and say, well, I can make this hydrogen happy, and I can make this hydrogen happy, and now everybody's happy, right? So what I have got going on here is I've got some bonding to a hydrogen, more bonding to a hydrogen, and some more bonding to this oxygen over here. All right, so just to clarify, I'm going to throw you guys a question or two here. So first question is, how is the carbon bonded to the oxygen? What's the best way to describe, if I ignore the hydrogens, what's the best way to describe this bonding between carbon and oxygen? All right, now that is, again, that would be a double bond because these two atoms, if I'm looking just at carbon and just at oxygen, they're sharing 4 total electrons. All right, what's the best way to describe the bonding between carbon and hydrogen? All right, we would call this 2 single bonds because I've got a single bond here and a separate single bond here. So there's 2 being shared with this hydrogen and 2 others being shared with this hydrogen. So what in this single example, we can see a single bond, another single bond, and a double bond. Okay, that's the main stuff I wanted to go over with you guys. I know it was kind of a lot all at once. Most of it is just kind of building on your knowledge base of how these electrons move around to make covalent bonds work. I also wanted to share, like I mentioned, so I'm going to give you guys 2 links right now. So here is a link for a Kahoot. Actually, I'll give you 2 links. One is for ionic bonding, and the second one is for covalent bonding. Those are just really good reviews. I'm not going to be tracking who did it and who didn't. It's just going to help you figure out, can I answer the most basic questions about this topic for class, which you should be able to do. If you guys have any questions, please reach out and let me know. And if you're in cohort B, I'm looking forward to seeing you in person next week in school. Have a good one.